Good day. Today we can discuss the topic about queuing theory model number 4. Before going into model number 4, we should aware about what is meant by queuing theory. Queuing theory is the study of the movement of people, objects or information through a line. If you are considered, you may standing in front of manufacturing industries means there are n number of jobs available for processing in particular machine or specific machines. So here the n number of jobs or customers and the particular machine is called as a service station. So how can we allocate the job to that particular machine for profitable manufacturing? And also we should estimate the probability of servicing time, probability of arrival time, probability of servicing time. Likewise we can estimate through this queuing theory. So the queuing theory has different models. Today we can discuss about model number 4. In queuing theory, Kendall's notation playing vital. So model number 4 has a Kendall notation as like m bar 1 colon FCFS bar n bar m. Here what is meant by first m? Yes. First m denotes the Poisson arrival or exponential inter-arrival time. Similarly, the Kendall notation has second m also. So, the second m denotes the Poisson departure or exponential service time. After that, there is one available. One means service provider for the customer. And then colon, again the open bracket is available. After open bracket, there is notation available as like FCFS. FCFS means first come, first served slash n. Here n represents number of customer already in the queuing system, which can be represented with small n bar small m. Small m represents total population that are available with the system. Here different models available. Why we need model number 4? Yes, in model number 4, population size is less than 40. We can utilize this model for solving the problem. There may be n number of population size is available, but in our model number 4, we can solve the problem with less than 40 population. In this model, calling sources is limited, which is the condition that we can utilize model number 4 for queuing theory problems. Formulas utilized for solve the queuing theory problem with the model number 4. Here the formula are listed. The first formula, probability that the system is empty. If the system is empty means we should identify the probability. So n number of jobs are available for processing, but the system does not consume any product for processing means the system is empty. So we should determine the probability that the system is empty also. For the reason P0 is equal to 1 divided by summation of small n is equal to 0 to m. Here the formula into m factorial divided by m minus n factorial into lambda by mu power n. Small n means number of customer already waiting in the queue. Small m means the population size, total population size. Then next, the steady state probability of n customer in the system, which can be determined Pn is equal to P0 into m factorial divided by m minus n factorial into lambda by mu power n. And then next important formula is expected number of customers in the system, which can be represented as like Ls is equal to summation of small n is equal to 0 to small m. Here, sorry, the notation is wrongly mentioned as capital N. Here we can utilize small m. N into Pn is equal to m minus mu by lambda into 1 minus P naught. And then fourth important formula is expected number of customers in the queue. LQ is equal to small m minus lambda plus mu divided by lambda into 1 minus P naught. So we can solve the queuing theory problem with the model number 4 by the utilization of these four formulas. How can we utilize these formulas for solving the problem? For understanding purpose, I may utilize this machine shop problem, mechanic shop problem. The mechanic repairs 4 machines. The mean time between service requirement is 5 hours for each machine and is exponentially distributed. If I consider, I may be standing in the car mechanic shop. In that 4 cars came for repair. So the mean time between service requirement is 5 hours for each car and is exponentially distributed. The mean repair time of a car follows the same distribution and is 1 hour. So the downtime cost of a machine is rupees 50 per hour, which means the repair time of the car, which is rupees 50 per hour. And for the utilization of mechanic, I can give to him a salary. For that, the mechanic cost is rupees 100 per day. Based on that data, I can determine the expected number of operating machine, expected downtime cost per day. Will it be economical to have 2 mechanics each repairing only 2 machines? These are all the questions available in front of me. How can I solve? First step is to collect the given data from the available problem. So given data here, according to this problem, the total population is available for servicing is 4 machines, so that small m is equal to 4. Arrival time of every machine is 5 hours. Arrival rate, so that I can estimate arrival rate as 1 divided by 5 per hour. From this I can estimate the lambda is equal to 0.2 per hour. Service time is equal to 1 hour. Service rate is equal to 1 bar 1 hour. So mu is equal to 1 per hour. So the exponentially distributed is called as lambda, and this distribution, the distribution repair time is mu. Likewise, we can collect the data from the given problem. After that, we can move to find the solutions. Moving the solution, carefully study the first question, expected number of operating machine. So how can we identify the expected number of operating machine in the available system? The formula is total number of machines minus number of breakdown machines. The total number of machines already we know because of problem gave data as like the mechanic repairs 4 machines, so that the total number of machines are 4. And the number of breakdown machines, no, the manufacturing industry doesn't know and the mechanic also doesn't know, so that we have to have estimate number of breakdown machines. So the mechanic expect the number of breakdown machine in the system, which can be determined through the formula of LS is equal to small m minus mu by lambda into 1 minus P naught. Here, according to this problem, small m I already know, the total population 4 machines. Mu also I know 1 per hour. Lambda is also I know from given problem as 0.2 per hour. But I don't know about P0 value. How can I identify P0? What is P0? P0 is the probability that the system is empty. So P0 can be determined by 1 divided by summation of n is equal to 0 to m factorial divided by m minus n factorial into lambda by mu power n. So here n is equal to 0 to m available. So initially the q is empty, so that n is equal to 0. Finally the m means the total population reached. According to this problem, the 4 machines are available, so that m is equal to 4 because total population size is 4. Okay. So likewise, we can first understand the problem and the formula notations. After that, we can move to solve the problem. So it's equal to, I can substitute the values 1 divided by the formula is like summation of n is equal to 0 to m. So first I can substitute 0 for every customer. Here the small n is equal to 0 because initially the system is empty, n, so that n is equal to 0. So capital small m, already I know about small m is equal to 4, which means total number of machines is 4. machines are 4. So that 4 minus 0 is equal to 4 factorial. So here you see m, small m 4, so that 4 factorial divided by 4 minus 0 is equal to 4 factorial I got into lambda. According to given problem, there is lambda is 0.2 per hour, mu is equal to 1 per hour. So that I can substitute 0.2 for lambda, mu is equal to 1, 0.2 by 1. What about small n? Here you see summation of n is equal to 0 to small m available. Initially I assume the system is empty, so that here small n is equal to 0. After that I move to next step, plus 4 factorial, because small m is equal to always 4. What about the small n? First customer enters into the service queue, so that n is equal to 1. So here small m is equal to 4 minus n is equal to 1. 4 minus 1 is equal to 3 factorial I got. After that lambda as usual 0.2, mu as usual 1, 0.2 divided by 1. The first customer is enters into the queue, so that here n is equal to 1. So that 4 factorial divided by 3 factorial into 0.2 by 1 power 1. Similar to same, I move to another incremental plus 4 factorials. Here also small m is equal to 4. What about small n? Next customer enters into the queue, so that small n is equal to 2. So 4 minus 2, I got 2 factorial here. 4 factorial divided by 2 factorial into 0.2 by 1 square, plus the next incremental of another customer came into the queue, which means another machine also comes into the service station. So 4 factorial, total number of machines according to the problem, m is equal to 4. 4 minus 3 is equal to 1. 4 factorial divided by 1 factorial into 0.2, as usual 0.2 by 1 power 3 customers are waiting in the line, 3 machines are waiting in the line, so that here 3, small n is equal to 3. Similar to same. Finally, the 4 machines are enters into the service station, so that here m, small m is equal to 4, small m is equal to 4 minus small n also 4, so that 4 minus 4 here 0 factorial. 4 factorial divided by 0 factorial, as usual 0.2 by 1, and power 4 customers are waiting in the line, already waiting in the line, so that small n is equal to 4 here. I simplify these mathematical numerical substitution in the mathematical formula. I can get P0 value as like 0.3982. Finally, I substitute this LS value it into the, P0 value here, sorry, which is P0 value in the LS equation. I can get, here see the formula, LS formula is equal to m minus mu by lambda into 1 minus p naught. Here m value, the total number of machines 4 minus mu, already we know 1, by lambda already we know about 0.2, 1 minus p naught. P naught determined with the previous step. So 0.3982. I substitute here 1 minus 0.3982 is equal to 0.9915 approximately, which is equal to 1. I assume like that. From this I can determine expected number of operating machine in the system, which can be identified through total number of machines minus number of breakdown machines. So the total number of machines available in the service station is 4. The determined expected number of breakdown machines in the system determined through LS as 1. Okay, 4 minus 1 is equal to 3. So the expected number of operating machine in the system 4 minus 1 is equal to 3. So one breakdown machine is available and 3 machines are good conditions to operate the performance. Likewise, we can determine through this formula. After that, expected downtime cost per day. What is the downtime cost, which can be identified through number of hours per day into expected number of breakdown machine into downtime cost into number of machines. Here we are having all the data. Yes, let's see number of hours per day. We can assume every shift consumes 8 hours, so that I can select the data like number of hours per day is equal to 8 hours. And then expected number of breakdown machine, already I determined. Expected number of breakdown machine is 1, already I determined, so that 1 into downtime cost. How can we identify downtime cost in problem? The downtime cost of a machine is rupees 50. The data is given in the problem, so that I can substitute 50. Number of machines, here number of breakdown machine is 1, so that here I substitute 1. So from this I can get rupees 400 as the expected downtime cost. Now you may aware how can we identify the expected downtime cost from the model number 4 formula. And then third question, what about the third question? Will it economically to have two mechanics each repairing only two machines? Will it be economical for having two mechanics for repairing two machines? Let me determine with the formula. Before going into the solving, we should aware about if the total cost with the two mechanic is less than the total cost with the one mechanic. When there are two machines, each mechanic serving only two machines, therefore m will be equal to 2. In previous step, we assume m is equal to 4 because total population has 4. Now we are having two mechanics, so that every mechanic consumes two machines for repairing the particular repairing service. So that here the population size is 2 for every mechanic. Likewise, I can assume, so that here the small m is equal to 2. Now you can understand why I put 2 as the small m, because two mechanics I am having, so that every mechanic I can allocate the mechanics to different machines with the 2. I can divided 4 machines into 2 for every mechanic. Okay, so here small m is equal to 2. Likewise, I can determine the P0 value. P0 value I can determine and get 0.6756. Likewise, I got the P0 value. From this, I can again identify the LS, because now I go for identifying the introduction of new mechanic in the shop floor, so that expected number of customer in the system I should again identify, which is LS is equal to m minus mu by lambda into 1 minus p naught is equal to, here small m is equal to 2, mu the same 1, lambda is the same 0.2, so that 2 minus 1 divided by 0.2 into 1 minus newly identified P0 value, which is 0.6756. I substituted here. From this I can get 0.3783. So newly identified LS value as 0.3783. From this I can identify the expected downtime per day from the formula of number of hours per day into expected number of customer in the system into number of machines. According to the splitted machines, I am having two machines. So for repairing the two machines, I am having 8 hours. The expected number of customer in the system I determined through this LS, which is 0.3783. So all the things I multiply with each other, I can get the expected downtime per day as 6.0528. So 6.0528 as the expected downtime per day. Why I determined this? Yes, I can determine the downtime cost from this. According to the given problem, the downtime cost of a machine is rupees 50 per hour. So that expected downtime cost per day is equal to 6.0528 into 50 is equal to rupees 302.64. If I utilizing two mechanic means downtime cost per day plus cost of mechanic. So downtime cost per day I determined through previous step, which is rupees 302.64 plus cost of mechanic. I utilize two mechanic means 2 into every mechanic consumes mechanic cost is rupees 100 according to our problem, rupees 100 per day. So 2 into 100. From this I can get to rupees 502.64 rupees for mechanic. If I consider only one mechanic for servicing the machine means the downtime cost per day plus cost of mechanic. Here I can't utilize the 302.64 as the downtime cost per day because I am utilizing only one mechanic, so I can pick the value from the previous step, which is expected downtime cost. If I here in this formula I consider the number of machines or one, okay, the expected number of breakdown machine 1, number of mechanic is 1, so that I can get 400. I can substitute here the cost of mechanic for the downtime cost per day is 400 plus cost of one mechanic is 100, so 400 plus 1 into 100 is equal to 500. Finally I make a decision as like it will be not economical to have two mechanic, because if I utilize two mechanic means I to be send rupees 502.64, so which exceeds the cost of one mechanic. The one mechanic cost is rupees 500, so that the economical number of manpower allocation to my servicing station is one mechanic, which can be calculated through this procedure. So now you may understand how can we solve the queuing theory problem with the model number 4. Thank you all. If you are having any doubts, you may ask me through the comment box. Thank you all.